who's Vivi Nastase, who is a research associate at the University of Stuttgart, working on semantic relations and knowledge acquisition, and was an organizer of the ESP workshop at NACL last year on extracting structured knowledge from scientific publications. All right, Vivi, everything good? Oh, Vivi, sorry, we can't hear you.
Can you hear me?
Yes, we can hear you now.
Sorry,
Awesome.
I was a bit confused.
No problem. All right,
so,
go ahead.
Thanks very much for the invitation to talk here. So this work is a little bit off on a tangent. We also started by analyzing scientific publication. In particular, we were trying to work with the ACL collection. And as most of you probably have experienced, we immediately ran into trouble in extracting exactly the kind of information we wanted. So we said, well, let's not waste time. And in the meantime, just analyze properties of graphs, so maybe we understand better the structures that we are trying to build. So knowledge graph, which is of course what we were after, have this dual functionality, right? So they provide knowledge for a variety of knowledge natural language applications, which is what we wanted to do with this extraction of information from the ACL collection. But they also have this very interesting structure, and they can provide a framework for us to try to develop some interesting methodologies while we are building our own KG. So our main purpose was two, actually. So we were trying to retrieve implied information, so trying to link a source and a target, going through various sources of knowledge, and of course this a bigger project of putting together the information from the ACL collection to discover existing and novel scientific hypotheses, or new ways to solve different problems. So like I said, then we focused on the structure of the knowledge graphs and trying to figure out how to work best with it and what kind of information is missing and how to add it back. And of course, when we are working with knowledge graphs, we usually use either the symbolic representation or the continuous representation, so their projection into an embedding space, or the two combine together. And this is very exciting, right? Because they are such different facets sort of the same thing. So what we did first was trying to look a little bit at knowledge graphs and figure out what is their shape, what is their structure, what's missing in there. So these plots here show you Freebase and NELL. So the top one is just the histogram of the node degrees, and the bottom one, the relation frequency. So you can tell already that there is a lot of structural imbalance in Freebase and NELL. So not just that they have missing links and missing nodes, so a lot of missing information, but this information is missing in an imbalanced way. So this was kind of exciting because it means there's something to try out there. And of course, the other type of dark matter are the negative edges. So we know that all the information knowledge graphs is the positive stuff, but where are the true negative edges? And we know those are important because we use them a lot for link prediction and other models. So the impact of these dark matters, so things that we don't see in there, is, like I said, the structural imbalance, the noisy negativity samples that we extract to be able to do link prediction and other approaches. And the consequence of that is that we obtain skewed entity and relation representation, and of course this impacts all the downstream applications. So there's not just dark matter in KGs, but there's also some hidden matter. So we call this information that's sort of there, but maybe not as obvious. So examples of such hidden matter would be the types in Freebase, which some people use, some people don't. The categories in NELL, which we know are there, not always exploited. Of course, there are also things that we have to look for. So types and categories are kind of provided, but there are also patterns that we kind of assume are there. For NELL, we know they are there because it was built that way. For Freebase, we can assume they are, but we have to look for them. And of course, there are various clues about negative edges. So there are things we can use. So we can discover first this hidden information in knowledge graphs and then use it to discover the dark matter. And of course, there's lots of information that I won't talk about here, but other people have. So for example, dependencies or connections between relations in Freebase, the information provided by their names of themselves, subgraph features and so on. But I will talk today about these first three aspects. And this is sort of the summary of my talk. So I would like to tell you about our experiments on finding different types of negative edges and how they impact link prediction. The same about types, so using types for better link prediction, and discovering some patterns and using them to find the new edges and also new nodes. So starting with the negative edges, so the task that we know is called negative sampling, right? So it's already used, frequently used in link prediction. We cannot do it without it. And what people usually do is use some heuristics. So these are four main heuristics. First one is random sampling. So you have a source relation target triple, and you replace the target with just some other entity in the graph, so any other node. Corrupting positive instances, so this one is a little bit more constrained, so we have the source relation target, and instead of the current target, we just take another target that appears in the same relations with some other source, and the same for the source. So for the type sampling, we do similar things. We just replace the target or the source with an entity of the same type. And for relational sampling, we use the positive instances for other relations as negatives. So these are frequently used heuristics. They have ups and downs. So random sampling, for example, is easier to obtain. The other ones need more checks, for example, but it's hard to, so they are not that good. Right? So we know from traditional machine learning that a model sort of is stronger if it has difficult negative instances to contrast with the positives. So we propose two negative sampling methods which are based on a learned model. So we use the latent factor model, in particular rescal, and we use the model, and we use this model to find hard negative samples. So what we did, we had two strategies. So one is nearest neighbor sampling. So for example, we choose for a triple source relation target, we choose sources that are very close to the correct one in embedding space, but it doesn't appear in the knowledge graph. And the second one is, we call it near miss sampling. So we choose a triple that is scored higher than our true positive sample. So we have these 6 strategies and we try them out. We try them out for FB15K and for WordNet 18. So they are 2 frequently used data sets, and they were used in some paper that we're comparing our results from. And we were quite surprised by the difference, the impact of these different negative sampling techniques has. So funnily enough, for FB15K, where the most common negative sampling technique is corrupting the positive instance, it actually performs the worst. So this near miss and nearest neighbor, they actually performed the best. For WordNet, actually, it didn't matter all that much. The performance was much closer, and it performed pretty well with the by corrupting positive instances. So sort of this work, which online I think has many more analysis if you're curious about it, it provided us with some interesting conclusions. So generally more negative samples are better. We also had, so in this previous one, the x-axis is the number of negative samples we use. So we started from 1, 5, 10, 20, 50, and 100. So we tested the number of negative samples, and of course, more negative samples are better up to a point. But we also, well, not surprisingly, but we saw that the method of sampling negative instances truly matters, and it matters not only in connection to the structure of the graph, but also the model learned. So I should have thought this better. So if you notice, so the first plot is for complex, the second one for distmalt, rescal, and trans-E. So there's a combination of the structure of the graph, the degree of imbalance that is in there, the relational model used, and everything together matters. So the combination actually matters. So negative sampling depends both on the data and the model. And this was an important lesson for us to learn. So how about the types then? So this is, like I said, the hidden information in the system. It has been used before to organize the sort of the adjacency matrices and try to optimize the model. We decided to add it as a separate factor in our relational model. So types are like you see here. So these are from FB15K. So every source has one or more types. So we can use these things. We use them in combination with rescal. So this is just for you to remember a little bit what rescal looks like. So basically, we are trying to approximate the adjacency matrix for every relation. We assume that each entity is modeled by a vector and the relation is a weight matrix. And every triple is a score that we obtain by multiplying the two vectors and the matrix. And typically, the loss function is the max margin, which contrasts the score of a positive instance with that of a negative instance. So we basically added to this loss function a score which is weighted by alpha, which we call the type regularizer. So this type regularizer basically just adds two more max margins that compare the scores of the source and the target with their correct and incorrect categories. And by adding type information, so our idea was that since the data is so imbalanced, so you saw FB15K has a lot of imbalance. There are a lot of entities that participate in very few relations and a lot of relations with very few instances. So all this information impacts the representation that we obtain. And if we compensate the lack of information with some type information, then maybe we get something a little bit better. So we did some experiments about that, and we varied the size of the training data, and we observed very interestingly that so the orange line is the one that has the regularizer. So for very little data, so for 25% and 50% of the training, the results are actually worse when we add the type regularizer. And this was initially a little bit surprising for us because we thought that's where they would help the most. But then when we looked deeper, actually what happens is that when a relation doesn't have enough instances, then what they learn, and we use type information, they learn relations between categories as opposed to relations between actual instances. So this was confirmed when we did experiments and we plotted this information on a 3D plot. So here the X and Y axis is the degree of the first and second argument, and the Z axis is the frequency of the relation. So what we want on the left-hand side is just the bilinear model, so rescal, and in the left-hand side is the bilinear model with the type regularizer. And what is good, the good thing that happens is you see this shift towards red of the values in terms of this is MRR, and the next plot is going to be hits at 10. So the results improve generally, and particularly for relations that have that connect instances with few relations. And also, so this is for hits, again, a shift towards 10. And the embeddings were improved particularly for low and high frequency entities. So it was funny that we get improvements for high frequency entities because you would think, yes, they have a lot of information, so they are kind of properly described. But the funny thing is it prevents overfitting. So it enforces these shared types, and then the embeddings for high frequency entities will be sort of more informative and more general a little bit. But on the negative side, it hurts performance for low frequency relation because, like I said, it introduces this bias towards learning relations between categories rather than more specific entities. But still, it was useful. So we continued to explore. And the next thing we tried out were patterns. So until now, we were concerned with leak prediction, so adding new edges, but of course we need some new nodes as well. And we were inspired by this work by West et al. From 2014, who used Google query logs to augment queries to find better extraction. So the idea was that, so their example was that if you want to find out who Frank Zappa's mother is, if you make a query, Frank Zappa mother, then you get this fragment that says the mothers of invention were an American rock band, and so on and so forth. And their idea was that query logs can provide additional information, so you can augment the query so that it is more constrained, right? So for example, if they add Baltimore, which is the place where Frank Zappa was born, then immediately you would get a better extraction. So our idea was that since we don't have access to Google query logs, knowledge graphs also contain associated information. So why not try to find it there? So the idea was to look for this kind of patterns in knowledge graphs, which were used for other tasks before, as alternative paths that connect the same sources and targets. So you have a relation R, it connects target S and T, for example, nationality. So the nationality of S is T. We can also find alternative paths that connect these two. So for example, X's place of birth is X, who is also the place of birth of Y, whose nationality is T. So SN has the nationality T. So as a more clear example, this is a relation instance. And so this is the kind of patterns we thought we could use to add information. So if we were to, if we wanted to find out what is Andris Berzin's nationality, we could add various types of information from this path. So these are the different query expansions that we made. So we can add just the source and the relation. We can add the other paths, relations on the path. We can add the other nodes on the path, or everything together. So we did some experiments. We used Google, of course. We relied on Google for some lexical variations. And what we found out is that by expanding, in approximately 60% of the cases, expanding the query with these patterns, with information from these patterns that we found in knowledge graphs, leads to better results than the baseline setting. It's not perfect though, so, and it wasn't also clear right at when we made the experiments, what strategy works best for different kinds of queries, like would more specific relations that are more constraining, do they need additional information, or they are the ones that work best with the relation? There was no apparent pattern, but we thought, okay, maybe the idea is to find, we could solve everything by finding better patterns. So what are the issues with patterns? We go back to knowledge graphs and their structures. The problem is that they are incomplete and also imbalanced. So some patterns will not appear, or maybe they will be weighed wrongly and they will seem unimportant. And also when we have very large knowledge graphs and we always want to make them even bigger, so this problem is not going to get easier in time, is that it's computationally very expensive. So our hypothesis was to try to look for patterns at a higher level. And we built these things that we called abstract paths and abstract graphs, from which we extract abstract paths which have some interesting properties, we thought. So to obtain this abstract graph, we basically combine the types with knowledge graphs. The precondition is that our knowledge graph has to have typed relations. We don't need to know the types, just to know that these relations sort of impose specific constraints on their arguments. So what we did is we built, this is a subgraph of fragment of Freebase, and the nodes represent abstract categories, which are basically just sets of sources and targets respectively for a relation. So the black edges are true relations from Freebase, and the blue edges are set relations between these domains and ranges. So how would it work? So we have this knowledge graph, which we know is imbalanced. We build this abstract graph, and from this one, we try to build abstract paths, which are just like the paths we saw before. So we have a relation between two nodes, and we want to find alternative paths between them. So this is actually a relation obtained from NELL, stadium located in city. So we did that, and abstract paths actually, they're very simple. They're just an intentional representation of the knowledge graphs, right? So the knowledge graphs are the extension representation because they just contain explicitly all the facts that we know about. So the advantage of making this representation is that we have a smaller graph to process. We don't have problems of traversal in there. And this general view hides any imbalances, and it will allow us to find, hopefully, better patterns. So this is the compression level that we achieved. We worked on Freebase and NELL. So these are the datasets used by Gardner et al. And you see, for example, the standard version of the knowledge graph has 20 million nodes, 67 million edges, and the abstract graph has like 4,000 nodes and about 22,000 edges, most of which are just the set relations. So PRA paths, which were the ones collected before, are just collected through random walks. And then node information was removed, and they become meta paths, and they are ranked based on frequency. So for abstract paths, we just generate the paths through traversal to connect specific nodes, and we weigh them depending on the strength of the set relations.
A couple minutes?
Yes, I'm done almost. Yeah, so here are some examples. So on top Freebase PRA path, and on the bottom Freebase abstract path. So the way Freebase paths work, they oscillate a lot between an entity and this type object link that moves them to another entity that has the same type as they do. So they look a little bit funny. And on the bottom, you see that we have, they seem much cleaner, and they kind of make a lot of sense, but are they good? So this is a little bit of information about the training test sets, and this is just to show you how hard the problem is, because the number of instances for training and testing varies quite a lot between relations. So these are the relations that we got. So we used these patterns first for link prediction. We got better results on NELL, and that was not surprising because NELL was sort of built on this idea that there are connections between relations, and that helps them learn relations together through this coupled learning. And the fact that our system sort of found out this, again, confirmed this, sort of gives us hope that these kind of abstract paths are useful. So this is it. We think that these abstract paths we found, at least when you look at them, and in some experiments, they seem more focused and informative. They improve link prediction on NELL. It didn't work as well on Freebase, but we didn't explore because there are lots of ways to weigh and score all these paths. So as a conclusion for paths, we think that it's useful to try and mine for such patterns, because you can use them internally to identify missing links, or more importantly, which is what we want to use them for, postulate novel paths to connect nodes, and this way discovering undiscovered knowledge, and also externally for targeted information extraction. So concluding conclusions, maybe I don't have to repeat them, but it's useful to investigate your data structure and know where its hidden and dark parts are, and use them for building a better resource. And that's it. Thank you.
All right, thanks, Vivi. We have time for maybe just like one quick question in the Zoom chats. I did have one question around, just curious, because most of the examples shown were sort of like NELL or Freebase. If you've seen any of these sort of phenomena, like any of these work also in like biomedical or scientific knowledge bases, like UMLS?
We haven't tried it on any domain-specific knowledge graph, but the code for all of these things is online. So if anybody is interested to try it out, then it's there. And of course, we only thought about our own narrow interests. So on this ACL graph that we were trying to build, and we haven't got there, so we haven't tried them. But yes, I think we should try it out.
Awesome. Thank you so much.